Hello and welcome to this lesson on reversible reactions. In today's lesson, we will understand the concept of reversible reactions and recognize the reversible arrow notation. So far, we've covered the basics of chemical reactions, understanding that reactants transform into products through various processes. Building on this foundation, today's lesson will advance our chemical understanding by introducing the concept of reversibility in chemical reactions. This will allow us to better comprehend how reactions can reach a state where both reactants and products are present simultaneously in a balanced condition. Let's get started. In most everyday reactions, we tend to think of reactions as irreversible. Once the reactants convert to products, the reaction stops. For instance, cooking an egg involves chemical changes that cannot be undone. You cannot uncook an egg. The transformation is permanent. However, many reactions in chemistry are actually reversible. They can proceed in both directions, from reactants to products and from products back to reactants. To represent this, we use a special notation known as the reversible arrow. The half arrowheads on each side of the double arrow signify the reversible nature of the reaction. The arrowhead pointing to the right indicates the forward reaction, where reactants form products. The arrowhead pointing to the left indicates the reverse reaction, where products revert back to reactants. One classic example of a reversible reaction involves ammonium chloride. When ammonium chloride is heated, it decomposes into ammonia and hydrogen chloride. If the products are allowed to cool, the reverse reaction can occur. In the reverse reaction, ammonia and hydrogen chloride combine to form ammonium chloride again. Therefore, this reaction is reversible. Let's also consider the reversible reaction between anhydrous copper sulfate and water. Note that anhydrous means the substance contains no water. Anhydrous copper sulfate is a white solid. When you add water, it reacts to form hydrated copper sulfate, a blue solid. If you heat the hydrated copper sulfate, this drives off the water and the reverse reaction occurs, regenerating the white anhydrous form. One important thing to note about reversible reactions is that the energy changes in the forward and reverse directions are always equal and opposite. This means that if the forward reaction absorbs energy, endothermic, the reverse reaction will release that exact amount of energy, exothermic, and vice versa. For example, if the forward reaction is exothermic with an energy change of plus 100 kilojoules, meaning it releases 100 kilojoules into the surroundings, then the reverse reaction will be endothermic with an energy change of minus 100 kilojoules, meaning it absorbs 100 kilojoules from the surroundings. Let's look at some extension knowledge on the conservation of energy. The reason why the energy changes in reversible reactions are equal and opposite is due to the law of conservation of energy. This fundamental principle states that energy cannot be created or destroyed, only transferred or converted from one form to another. In any chemical reaction, the total energy in the system and its surroundings remains constant. In the context of reversible reactions, if the forward reaction is exothermic, energy is released into the surroundings. For example, heat. This energy has to come from somewhere, specifically from the reactants as they form products. When the reverse reaction occurs, energy must be absorbed from the surroundings, endothermic, to revert the products back into reactants. This is because the reactants need to regain the same amount of energy that was released in the forward reaction to return to their original state. Understanding reversible reactions is crucial in both laboratory and industrial settings. In industries such as fertilizer production, reversible reactions are used to optimize the production process. For example, the Haber process, used to synthesize ammonia from nitrogen and hydrogen, is a key industrial application of a reversible reaction. We will examine the Haber process in more detail in an upcoming lesson. In today's lesson, we delved into the concept of reversible reactions, where products can react to reform the original reactants. We learned that reversible reactions are represented by a special notation, the reversible arrow, indicating that the reaction can proceed in both the forward and reverse directions. We examined the dissociation of ammonium chloride, and the hydration of anhydrous copper sulfate as examples. We also discussed energy changes in these reactions, understanding that they are equal and opposite. By understanding reversible reactions, we gain insights into how various chemical systems behave. In upcoming lessons, we will see how we can manipulate these reactions to produce desired results efficiently. Watch the rest of the GCSE Chemistry course at Sophos Education.